Thank you. Talk about lowering expectations. So I'm really delighted to be here. It's wonderful. It's my second time in Haifa, and the first time was memorable, and I have every reason to believe that the second one will be at least as good. And it's already starting great because I can feel back in touch with my Italian roots with this Madonna kind of setting that you guys have set up for me. So the work that I would like to describe today is actually motivated by something that occasionally happens to all of us. And you know, being the scholars that are faithful to the academic ideal, there is only one thing, of course, that we should be doing. So suppose that we actually decide to start a company, then you know, there are a lot of things that you have to worry about. But at some point, you actually have to start building the thing, and down the line, you may actually start asking yourself, which kind of database should I be using? And if coming to market quickly is a concern of yours, then what you probably want to do is to come up with, pick a simple solution that is going to optimize for ease of programming and for ease of debugging. And so you're probably going to use some kind of relational database with, ACID guarantees. And by that, I mean that it's a database that uses transactional database. So you have this transition of the state of the database that satisfy the 4 ACID guarantees. Atomicity, that says that either all changes happen or no change happens. Consistency, that says that if you start from a state that is a correct state, namely a state that satisfies whatever invariant are important for your state, then the transaction is guaranteed to transition the state to another correct state. Isolation regulates which of the intermediate states that are generated as the transaction executes is actually going to become visible to other transactions that are executing concurrently. Here, the gold standard, of course, is serializability, that says that none of the intermediate state actually becomes visible, and a series of, the result of executing a series of transactions concurrently is equivalent to some sequential execution of that set of transactions. And finally, durability, that says that committed transactions like diamonds are forever. So everything works well until you're actually successful. And you were dreaming about the fact that everybody was going to come and use your system, and now that it seems that almost everybody in the world does, then the very properties that were making the choice of an ACID relational database a good idea when you were first developing your system can actually feel like a straitjacket. And that's, as Alex was pointing out, that's why there has been a different kind of approach that people have started looking at over the last decade or so that goes by the name of BASE. And BASE has some, it's an acronym actually, basically available, soft state, eventually consistent. It's actually a geeky thing to say not ACID, right? And the idea of BASE is to actually renounce the transactional storage and actually rely on a much simpler API. For instance, in a key-value store would be something like put and get, and actually use custom code to actually try to squeeze every ounce of concurrency at the application level. And in fact, the challenge of dealing with concurrency, the challenge of dealing with failures, the challenges that isolation, for instance, was trying to address for us in the ACID model are actually moved to the application. And as you can imagine, the complexity of actually getting this right without introducing bugs quickly gets out of control, because you have to think about all the possible interleaving that before isolation was sort of transparently handling for you. But now, if you're moving things at the application level, you have to worry about. So it seems that then developers these days are actually facing a pretty stark choice. They can either decide to live on the desert island of ACID, in which you have ease of programming but limited performance potential, or you can live on the desert island of BASE, in which the potential for performance is high, but the complexity that goes with realizing this potential can often be prohibitive. And bad as this may be, these options, it's not like there is a lot of stuff in between that can turn out to be useful. And so the question is this really our lot, or, or is there something better that we can aim for? And so what I would like to discuss with you today is what we have been doing in our search for this, this wonderful land with a system that we call SALT. Because we are geeks as well. I mean, no one comes second. And the idea of SALT, of course, is that it's what happens when you try to bring together acid and base. And what we're going to try to do is to try to see if there is a way to bring together the best properties of both. In particular, we're going to try to achieve, hopefully, most of the performance benefit that come with base at a fraction of the complexity that base typically requires. So if I go to the outline of our talk, of my talk, first I'm going to try to tell you what is that gives us a hope that we may be able to find that wonderful land. And it turns out that key to actually realizing the opportunity that I'm going to try to present to you is going to be a new abstraction that we call base transactions. And the central property of base transaction is a new isolation guarantee that we call salt isolation. And I'm going to describe to you what salt isolation is, and I'm going to quickly describe to you what are the mechanisms that we are putting in place in order to achieve salt isolation. And finally, I'm going to discuss a little bit of what salt isolation and in general, SALT buys us to see if we are, able to fulfill this vision of trying to bring the best of acid and base together. But first, I'm going to start, discussing what is the opportunity that we saw to try to make progress. And so it turns out that to try to make progress, we turned to this gentleman. And you know him, even if you don't know him. His name is Pareto, Wilfredo Pareto, and you all know about the Pareto Principle, right? The Pareto Principle says that when you consider a system, it's not the case that the effects that you see in the system are uniformly explained by the causes. There are some of the causes, in fact, in the Pareto formulation. 20% of the causes is responsible for a majority, an overwhelming majority, 80% of the effects. In fact, in computer science, sometimes we even have a more extreme version of the Pareto Principle, this 10-90 rule. And we actually, our experience is that, in fact, if I try to apply the Pareto Principle to this database system, we actually see that truly not all transactions are created equal. There are going to be a few transactions that are going to be the one that are going to be sort of testing the performance limit of the acid paradigm. But the large, overwhelming majority of transactions is actually not going to be problematic because for a number of reasons. For instance, they may be transactions that run infrequently, or they may be transactions that are short or that do not introduce a lot of contention. So if it is indeed the case that not all transactions are created equal, what opportunity does this present? Well, suppose that we were able to actually identify this performance critical transaction, which hopefully are going to be a few. And we were able to somehow BASE-ify, whatever that means, only those performance-critical transactions, leaving the remaining transaction completely unaffected. So the hope then is that we may be able, since we are BASE-ifying the transactions that matter for performance, we may be able to reap most of the benefit of moving to BASE, but at a fraction of the complexity, because a large number of the transactions would be completely unaffected in terms of their logic from the actions that we are taking. Okay? So that's the general idea. So how could we try to achieve something like this? How could we try to achieve greater performance? Well, to achieve greater performance, we have to allow for more concurrency. And a naive way to allow for more concurrency would be to take transactions and just chop them, right? So for instance, I could take this, so let's look at this transaction. This is a transfer transaction that actually checks if the checking account has enough money, and if the checking account has enough money, it actually transfers $10 from the checking account to the saving account. And for a moment, let's say that this is a performance-critical transaction. So what I could do in order to improve concurrency is actually chop it so that it splits into two parts, one that deals only with the checking account and the other that deals with the savings account. And the advantage of doing that is that if I'm trying to execute these transactions, instead of having to execute them sequentially like they would otherwise, what I can do is actually overlap the steps that take place with the savings account of one instance of that transaction with the steps that take care of the checking account with another instance of the transaction, right? So you look at something like this, and probably all of you are thinking, yeah. So the problem with this naive approach is that, of course, there is actually complexity that is brought into the picture once I'm chopping, because it's not that the transfer transaction is the only transaction that is running. Say that there is another transaction that is running, the balance transaction. And this transaction runs very seldom, so it doesn't have really any effect on the performance. But it does have an effect when it comes to the consistency of the database. So if I consider the transfer transaction unchopped in its original state, there are only two states that, not only, these two states are actually visible to the balance transaction, the state before the transaction transfer starts and the state after the transaction completes. And actually that guarantees that a transfer of money from checking to saving is not going to change the total amount of money in my combined accounts. But if I'm chopping and I'm exposing this intermediate state, then, as you can see, what may happen is that the balance transaction may actually compute the incorrect balance. And that's actually an indication of a broader problem. Here you see just by chopping a performance-critical transaction, that may actually affect the correctness of transactions that are not performance-critical. In fact, when I'm doing such, if I were to chop somewhat naively and try to achieve finer isolation through chopping, that actually may affect the correctness of potentially all the transactions in the system. So whenever I try to do something like this, I have to start thinking, okay, let's consider all the possible interleaving with all the transactions and see what happens. That's actually why the BASE approach can turn into a nightmare. And it seems that this is a fairly fundamental problem because, look, if you want better performance, you have to allow for a greater amount of interleaving, a greater level of interleaving, because you want greater concurrency. But if you are allowing for greater number of interleavings and greater concurrency, the chance that complexity grows because you have to think about all the possible interleaving. So in a way, a greater number of interleavings giveth, and a greater number of interleaving taketh away. In one case when it comes to performance, and taketh away when it comes to complexity. But here is where the observation that transactions are not created equal can help us again. If you think about it, in the cost-benefit balance, once again, transactions are not all created equal. For most transactions, having the ability to see more interleaving is going to produce complexity, because I have to think about the balanced transaction. I have to think about, well, what happens if I'm running balance and I've been exposed to this intermediate state. But it's not going to return very much, if anything at all, in terms of performance. So then the question is, if we have to do more interleavings, why instead of doing more interleavings indiscriminately, why don't we instead try to allow more interleaving selectively, so that only the transactions that actually can return some benefit in terms of increased throughput are going to be able to see those intermediate states, while transactions that would only become a headache because I would have to think about their correctness, and by seeing the intermediate state would return nothing in terms of correctness, well, those transactions are actually not going to see the intermediate states. So that reasoning about them is going to continue to be as simple as it used to. Basically, why don't we pay the complexity cost only when it's going to bring a return in terms of performance? So if we were to do that, then there would be a hope that we may be able to get performance, most of the performance, with a little cost in terms of complexity. So in this scenario, then, this intermediate state might be visible to another instance of transfer, but would not be visible to balance, so that I would be able to have interleaved executions such as these. Okay, that would still be okay when it comes to correctness and would give me more performance. So, as I was mentioning in my introduction, the key to achieving this result is going to be this abstraction that I call base transactions. So actually, base transactions refine traditional transactions. In traditional, what is beautiful about traditional transactions, one of the reasons why they are so successful, is that they are packaging in a single package these 4 properties that we saw before. And they are simple to use, in a way, that's some of their beauty, because these 4 properties are provided at one level of granularity, the granularity of the transaction. The flip side, though, is that if I chop a transaction, I'm not only chopping the transaction does not only give me finer granularity of isolation. It gives me also finer granularity, for instance, for atomicity, which means that a number of operations that I may want logically to either all occur or none occur, now I don't have that guarantee anymore once I chopped, right? So what I would like to do, ideally, would be to actually decouple the properties, the 4 properties of transactions, so that I can provide one of these properties as a finer level of granularity than I may be able to provide the others. And in particular, I may want to provide isolation at a finer level of granularity selectively, while I want to maintain atomicity at the coarser level of granularity, because that's what makes logical sense. So if I try to decouple, it turns out that there is a natural way to decouple the properties of transaction, and that natural way is nested transaction. If you think about nested transaction, when they were initially introduced, were actually introduced to decouple atomicity and isolation because they were actually thought as a way to handle long-running transaction. If you have long-running transaction and you have at some point an abort at some point during the long-running transaction, you don't want to have to roll back to the very beginning and restart. What you wanted to be able to do was to sort of take, allow me to call them, intermediate checkpoint along the way through the nested transaction, so that if you fail at some point in a transaction, you only go back to the sub-transaction in which the abort has occurred, not to the very beginning of the outer transaction, right? So they were actually decoupling atomicity and isolation in order to provide finer granularity of atomicity, while they wanted isolation to be at the level of the outer transaction, because they didn't want to think about all the nightmare of thinking about the interleaving that would occur if you exposed the intermediate state produced by subtransactions to the outside world. We want to also use nested transaction, but for, not for finer grain atomicity, but rather for finer grain isolation. And the way in which we're going to do it is we're going to take a transaction, and we're actually going to, if you want, split it in a number of sub-transactions that, again, pardon the geekness, we're going to call alkaline transactions. So now the original acid transaction is going to be split in this alkaline transaction, and those alkaline transactions are the basic building block of base transactions. And base transactions have actually two really nice properties. The first is that they continue to provide atomicity and durability at the same granularity of the original acid transaction that is being BASE-ified. Okay? So if I wanted to have the logic of atomicity maintained, I'm going to be able to achieve that. The other nice property is that it's going to actually able to support selectively, if you want, it's going to support the ability to export different granularities of isolation selectively so that the isolation that this base transaction is going to export is going to be different depending on which type of transactions it is interacting with. So let me try to go into a little more detail, but the intuition is fairly simple. If a base transaction, remember base transactions are what I'm producing once I take one of the performance critical transactions and I'm trying to massage it so that I can get performance out of it. So when a base transaction interacts with a base transaction, the intermediate states that are produced at the boundaries between two consecutive alkaline transactions are going to be visible so that a greater number of interleavings will be possible. When a base transaction interacts with a transaction that is not performance critical, with a transaction that we have kept as acid, then the only states that an acid transaction is going to see are exactly the same state that it was seeing before. So I don't have to worry about the logic of the acid transactions, how it is modified by the fact that we have BASE-ify. And the key to all of this is this isolation property that I call salt isolation that looks like a little bit like this picture here. If you look at it, and if you tilt your head on one side, it looks like a duck, and if you tilt your head on the other side, it looks like a rabbit. And salt isolation is a little bit like that. To base transaction, salt isolation guarantees that to base transactions, so to other transaction, performance critical transaction or other instances of a performance critical transaction, a base transaction is going to look as a sequence of small acid transaction, what I called alkaline transaction. To instead acid transaction is just going to look, a base transaction is just going to look like an acid transaction. It's going to see no difference. Okay? And hopefully, the idea is that that is going to allow us to get the best of both worlds. So let me tell you something more about salt isolation. We are actually going to, we are focusing on isolation guarantees that are lock-based isolation guarantees because we are thinking about databases that have high contention, and if I have high contention, a lock-based implementation is preferable to an optimistic concurrency control. And if the challenge here is if I want to have some formulation for salt isolation, it turns out that when I talk about acid, I'm really not talking, most systems that you see outside don't really provide, sometimes they don't even provide serializability, right? Instead, they provide weaker notion of isolation that are still called acid, and there are a number of them. Some, they have sort of a Voldemort kind of nature that they don't even have a name because people are so terrified by them, by allowing dirty rights. But as you can see, there are a number of different possible isolation, with serializability being the strongest of them in that it prevents all the bad phenomena that some of which are actually allowed by this weaker notion of isolation. So if we want to define salt isolation, we don't want to have to define salt isolation for read committed, salt isolation for read uncommitted, salt isolation for serializable. We would like to be able to have a single way to express salt isolation that can then be expressed for these different isolation guarantees. And to see how we did that, let's focus on just one of these isolation flavors that turns out to be fairly popular, actually quite popular. Read committed. Read committed gives you a promise that it's going to allow neither dirty reads nor dirty writes, but it also admits to its weaknesses. It says, yeah, no dirty reads, no dirty writes, but I cannot promise you the ability to have repeatable read. Namely, what may happen if I have read committed is the following anomaly. I may actually read a value during, while I'm I'm executing a transaction, I may actually read the value of x at some point and get some value. And then during the same transaction, I read again the value of x and I may get a different value. Okay? That's typically, surprising. It certainly shouldn't happen with serializability. Read committed allows it. So if I trying to express what property read committed provides, it's actually a property that says that if I have an update of, so if there is some transaction that performs an update, say on variable x, and there is another transaction that performs some operation that conflicts with that update, then read committed gives the following guarantees. If the update completes before either of these two operations starts, then the transaction to which the first operation belongs must decide before either of these two operations starts. Okay? That's actually, if you look at it, that's actually the guarantee that read committed gives you. So remember, what we are trying to do is to come up with a formulation that is going to be general. So let's try to generalize this statement a little bit. Instead of focusing just on this write operation, let's just say if I have an operation on the first transaction that completes before some other operation that conflicts with it in the second transaction, then I would like the first transaction to decide, either commit or abort, before the second operation starts. Slightly more general version of. And allow me actually to generalize it a little further by saying that the first operation may belong to some set of operations, and the second operation, the green operation, may also itself belong to some set of operations. And it turns out that that's all I need in order to be able to express all these different level of isolation that I was describing to you by appropriately instantiating those two sets, L and S, that I was showing to you, the sets to which the first transaction can belong and the second transaction can belong. In particular, it turns out that I can express all isolation levels by, again, appropriately instantiating L and S. And this becomes just a single way to express all these different levels of isolation. Okay? So then, if this is the isolation property appropriately instantiated, it turns out that what salt isolation can guarantee is that whatever is your isolation property, the isolation property that was holding before between all ACID transactions, this isolation property will continue to hold as long as both T1 and T2 are not both base transactions. So what does that mean in practice? That means that if you are an ACID transaction, you continue to be isolated from all other transactions just like you were before. If you have one of these alkaline transactions that are inside the base transaction, that are the, if you want, the building blocks of a base transaction, alkaline transactions are mini acid transactions, if you want. They are completely isolated from other acid or alkaline subtransactions that may exist, may be running concurrently in other transactions. And instead, base transactions are going to selectively expose the intermediate, the states that are in between the subtransactions that comprise them. Selectively, because they are going to show those states only to other base transactions. the mechanism that we're going to be using in order to implement this, this illusion of, or if you want, this abstraction of salt isolation is locks, just a single mechanism, locks. Of course, acid transaction use some kind of lock that I'm going to call an acid lock in order to be able to guarantee the properties that they provide. We are going to use two more flavor of locks in order to achieve our result, alkaline lock and saline locks, lots of locks. Let's actually see in detail what they mean. You're all familiar with acid locks. If I have an acid transaction that tries to update a variable x, what it's going to do is actually to acquire a lock, an acid lock, at the beginning of the transaction. Is going to keep it until the end of the transaction, so that if another transaction tries to read x, it's going to actually have to wait until the first transaction completes, and only then is going to be allowed to execute. So if I look at a table that expresses the conflicts between these different locks, you see that, of course, read-read operations don't conflict, but every other combination you have a conflict. Okay, but what about the locks that allow my base transaction to look like a duck and look like a rabbit selectively? Here, let's consider for a moment that the first alkaline transaction. Okay? If there is another base transaction that is concurrently executing, that base transaction should not be allowed to actually read the value of x while we are running the first alkaline transaction, because remember, alkaline transactions are isolated from all others, as if they were mini-acid. But it's actually going to be allowed to execute and see that intermediate state right there. An acid transaction, instead, of course, will not be allowed to execute during the first alkaline transaction, but also should not be allowed to see the intermediate state until we get to the end of the base transaction. So that's where these saline lock and alkaline locks are going to play a role. The alkaline lock is the lock that is going to actually protect, if you want, the isolation of alkaline transaction. And the saline lock is the one that is going to allow base transaction to be completely opaque to acid transaction, but selectively open the kimono for other base transactions. So let's actually look at saline locks. Let's actually look at their behavior in a little more detail. So here, as I was saying, there is going to be an alkaline lock that is going to be executed here. Alkaline locks should be such that the internal of an alkaline transaction is completely invisible within the limit of whatever was the isolation property that we were trying to implement. So in other words, the only situation in which alkaline locks don't conflict with other alkaline locks or acid locks is if both operations are read. Right? Read-read is not a conflict. So I'm not going to have conflicts at those entries in the table, but every other entry in the table is going to be a conflict. Okay? When it comes instead to saline locks should only prevent acid transaction from seeing those intermediate states. To other kind of transaction, either alkaline or base, saline locks are invisible. They're very visible for acid transaction that they don't, they can't mess with saline locks. But the other transactions are not going to see any effects from them. So this is what the saline locks does. And so again, a saline lock, when interacts with acid, is going to have a conflict, except for in the read-read case. Right? And for all the other entries instead, there's going to be no conflict. It is as if saline locks don't exist. Great. So you may say, well, so great. Are we done? Well, it turns out not quite. It turns out that there are some subtle problems that can arise. So for instance, despite all of our work, if I just stop here, it may be the case that acid transaction can actually read uncommitted values, which is really a no-no. We don't want that to happen. How could that be possible? Here is a scenario that would allow that to happen. You see that there is base that the red transaction is updating X, and the green transaction is reading X, and then is copying X into Y, and the ACID transaction is reading Y. So what may happen is that the red transaction has the first alkaline transaction complete, so the update completes. That allows this base transaction, the green transaction, to actually read X, it's allowed to, and copy it into Y, and then commit. And ACID is going to be perfectly happy. It's reading a committed value. And so it may actually, as a result, read the value of Y, which is actually the value of X, despite the fact that the original red transaction may not have committed yet. So I'm not going to tell you how we deal with this, but it turns out to be very, very simple and very, very efficient, and it's just one of the many, many pleasures you're going to have by reading our paper. The bottom line is a theorem. You know, all good stories end with a theorem. And here we can actually prove that given isolation level I, whatever is your isolation level, salt isolation is going to protect all acid transactions through effects, either direct or indirect, that may have, again, acid transactions are going to be completely unaffected by the fact that we are BASE-ifying. So how does this actually work? Does it actually deliver on what we were trying to achieve? So there are two questions that one may ask. The first is, what kind of performance gain does salt actually give us when I compare it with acid? And the other thing that you may ask is, okay, fine, how much effort is required in order to be able to achieve whatever performance you're going to show us? And here I'm reporting results that we have obtained in this particular configuration. We have looked at a bunch of micro benchmark and then two workload, TPCC, which is basically, I was asking my database friends, what kind of application do you guys use in order to convince each other that something works? And they said TPCC, which is kind of sad. No offense to the database people, but it would be nice to have something a little more, a wider range. So we also use Fusion Ticket, which is an open source ticket buying application that is used by over 80 companies. It's a fairly large system. And here are some of the, so here is the result that we obtained for Fusion Ticket. This is a latency throughput graph that actually shows you that acid sort of bottoms up when it comes to throughput at around slightly more than 1,000 transactions per second, while as you can see, salt actually doesn't bottom out until something like 7,000 transactions per second. So you have something like a 6.5 factor in terms of additional throughput that salt is able to provide. One thing that you may notice here is that if you look at the, when there is no contention, the latency that salt experiences is actually higher than the latency that traditional acid experiences. We have implemented this on top of MySQL cluster. So we actually, to implement salt, we took MySQL cluster and got into the guts of it and changed it so that it implemented the system that I'm describing to you. Well, it turns out that although MySQL cluster says that it implements acid, it really doesn't. It implements ACI, okay? No durability. And so instead, what we actually implement is, we implement the D as well. And so that's what explains the extra latency that you pay here. If you introduce the D also in MySQL cluster, you will actually see the same kind of latency that we are experiencing. What about programming effort versus performance? This is really the next to last slide. Programming effort versus performance. here you can see the kind of performance that we are getting in Fusion Ticket. Just changing one transaction. This is a system that has tens and tens of transactions. Even just the logic for buying a ticket is 12 transactions. We actually modify one transaction, this performance critical transaction, and we are able to get this level of performance. How good is it? Well, we didn't want to go through the effort of actually BASE-ifying 12 transactions because complexity grows exponentially as you are increasing the number of transactions that you have to BASE-ify. So what we said is, okay, let's take the transaction and just chop them. Forget about correctness. We don't care about correctness. We're going to just chop them and just run the thing and see the kind of performance that we get. That's an upper bound of the performance that we can get. That's what the column with raw operation talks about. And the factor that we get is, it shows that even by BASE-ifying one transaction, we get within 90% of what we can get by BASE-ifying the whole thing. So that's the end of what I wanted to tell you. So I try to argue that there is a pain point when it comes to transaction design. There is this new abstraction that we have introduced, base transaction, that relies on this salt isolation with this funding property, and it turns out to be somewhat promising when it comes to performance. And, perhaps. And I'm just going to end by showing you some of the people that work on this. Manos has been, it's going to appear in the next version of The Godfather. No, it's, he's just got married, and so that's why he's like this. Yang is an assistant professor now at Ohio State. Chao and Chenzhe are still working with me. Prince, as you can see, works at Google. And Navid has moved to better pastures. That's the end of my talk.